Okay, so because energy and heat are such an important thing when it comes to either producing or breaking apart certain compounds, we've actually investigated a lot of different compounds throughout the years and have come up with a list of standard enthalpies of formations for numerous compounds. What these things are is take any general compound, let's just say for instance chromium oxide, and we have figured out how much energy it'll take to either create this chromium oxide from its individual elements, so from the chromium and from the oxygen. And we've figured that number out. We actually published that number. It is in a list, and we could always reference that number if we'd ever need it. Okay. Yesterday, you'll remember, or Friday, remember when we did Hess's law, we had a whole bunch of equations that went along with each problem. And some of these equations, like for water, for instance, it was, 1/2 O2 plus H2 yields H2O, and then we had a number associated with that. That would have been the standard enthalpy of formation for water. So standard enthalpy of formation is just the change in enthalpy. So again, let's remember what that means, change in enthalpy. The change in enthalpy again means the heat flow, right? So the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard states. I'll get to that last section, this section right here, in a second. Let me just give you an example, though, quickly, of an enthalpy of formation. Let's go back to that chromium example, Cr2O3. Chromium oxide is a solid. So if we form that from its constituent elements, we'll have some chromium. Chromium is a solid metal, plus oxygen. Remember, oxygen is diatomic and a gas at room temperature. So if we got to balance this out, we'll have a 2 here and a 3 halves here. And notice the way I balance. I want to keep the oxygen or the chromium oxide on the right side to simply having 1 mole. Okay, I just want 1 mole there. And the reason is the standard enthalpy of formation is defined as formation of 1 mole of a compound. So we've gone through experimentation, and I say we, I mean scientists have gone through experimentation to figure out how much energy it actually takes or how much energy this actual experiment gives off. And if we take some chromium solid and we burn it in oxygen gas, this process is actually quite exothermic. It'll actually release about 1,123 kilojoules per mole of chromium oxide. So a very exothermic process, a very warm process. All right. Now let's get back to that thing that I said before, this standard state idea. If you look up in the symbol that we're using for standard enthalpy of formation, this guy right here, you'll notice that there is a degrees symbol right up there in the upper right-hand corner. That's got nothing really to do with temperature. That just refers to, that degree symbol refers to this phrase right here, standard state. Okay? Standard state needs to be defined for these things because if we change the pressure, if we change the physical state, solid, liquid, gas, if we change the temperature of these products or these reactants, that actually changes the way they act, the way they interact. And that actually would change their heat that they either give off or they absorb. So we have to actually define a standard state. We have to say, okay, if all conditions are equal, if all pressures and temperatures and phases essentially are equal, what would be the heat that's either absorbed or given off to form this particular compound? So that's what it means for standard state. So it's important to understand what those definitions of standard states are. So let's look at a compound. Let's just pick any old compound. Let's pick carbon dioxide. Okay, for a gas, the pressure is exactly 1 atmosphere. So the pressure on this CO2 would be 1 atmosphere. For a solution, the concentration is exactly 1 molar. So if we had, I don't know, a sodium chloride solution, NaCl, the solution concentration would be 1 molar. If you're a pure substance and use a liquid or solid state, it's just that that material is in its pure state. It's not mixed with anything else. So brass, for example, we wouldn't calculate a standard enthalpy for brass because it's a mixture of 2 metals. Okay, we could calculate for copper and zinc separately. Now for an element, it's just the form that element that exists at 1 atmosphere in 25 degrees Celsius. Okay, so nitrogen at 1 atmosphere in 25 degrees Celsius, which is about the conditions that you're feeling right now as you sit in front of your computer. For nitrogen, that's in the gaseous state. Okay, the gaseous nitrogen is around you right now. It's hitting you in the head. It's not solid. It's not liquid. For potassium, okay, potassium is in the solid state at 1 atmosphere and 25 degrees Celsius. So those are the conditions that we have to set for the standard state. Now, one other thing that's important to note about elements. When you have an element inside of a chemical reaction, it doesn't take any energy to make that element. That element's been made. The star exploded billions of years ago to produce that element, to produce that atom. So there's no heat of formation for elements. So if you had, for instance, potassium inside of your reaction, there's the heat of formation, the delta HF degree symbol equals 0. It doesn't take any energy to make that. You do need to understand that that goes across for like diatomics too. It doesn't take any energy to make O2, Cl2, F2, I2, any of the other diatomics that we may have. They naturally form those things because they're more stable, they're happier in those circumstances. So the heat of formations of any elements is going to be 0. Okay. Now, like I said, scientists have figured out these heats of formations. They put them in a table for us, and we actually have that table in our textbook. This is Appendix 4 in the back of your book, and it gives you the substance and state, and it gives you a bunch of different numbers in this appendix, and for this chapter, we're only focusing here. We'll hit the other 2 columns in a later chapter. So those are our standard heats of formation. Notice, again, they're in moles. So for 1 mole of barium sulfate in the solid form, if we want to form barium sulfate from its constituent elements, barium, sulfur, and oxygen, it will actually, that process will release a total of 1,465 kilojoules. That's quite impressive. That's pretty toasty. Okay. So we're going to refer to that appendix quite often. Let's look at an example. The burning of methane. All right, the burning of methane. So you take some methane, CH4, and you turn that into carbon dioxide and H2O. Now, in the last chapter, in 6.3, we used Hess's law because, and this actually is an application of Hess's law, but we used Hess's law to calculate out the total delta H for a reaction like this. And we had all these little mini equations that we used. We combined them by multiplying by an integer or flipping them and reversing them and flipping their sign for delta H. And then we got total delta H for the reaction. What I didn't tell you in that chapter is that if we were to happen to know the standard enthalpies of formation for all of the compounds involved, and I don't highlight O2 there because it is elemental. But if we know all the standard enthalpies of formation for all the compounds involved, we can actually really simplify that Hess's law process. We don't have to write all those little equations and flip them around and multiply by integers. Instead, we can do the following. We can ask to calculate what's called the delta H of reaction, which is essentially the same delta H that you calculated in Hess's law. Delta H of reaction takes a look at the standard heats of formation of all of the products and all of the reactants involved. So if we look at the standard heat of formation for the carbon dioxide and the water, right here. Okay, those are our products. And we look at the standard heats of formation of all the reactants, right there and right there. Okay, we can add those up, we can add those formations up, and we can actually come up with a resultant number for your for your equation, so your delta H. So in order for this process to occur, when methane is combusted, when it burns, when it heats your home, it releases 891 kilojoules for every 1 mole of methane that you provide. So it's quite an efficient process. Okay, so let's actually do a reaction like that. These are just some problem-solving strategies you can use. They're similar to what you saw yesterday, so I'm just going to go through them real quick. So here's your reaction. This is your total reaction for this particular process. The delta H of reaction, okay, the heat flow for this particular reaction is going to be equal to the sum of the products, delta H's, and the sum of the reactants, delta H's. That's our reaction. This sigma here, this guy means sum. Okay, that means just add them up. And let's do a problem. Let's do a sample problem. We're going to calculate delta H for the following reaction. So sodium plus some water equals sodium hydroxide and hydrogen gas. We've seen this demonstration before. Now this is a nice reaction for us because there are some things that we can actually eliminate. You have two materials that are elemental. And so you know right away that their standard enthalpies of formation are going to be 0. So they don't really partake in the reaction at all. So that guy can go away, and that guy can go away. So that leaves us with only two things that we need to worry about. That's sodium hydroxide and water. Okay, so it's products minus reactants. So we got to find the standard enthalpy of sodium hydroxide. And if you looked in Appendix 4 of your book, you would find that was negative 470. And for water, that's negative 286. So I'm going to go to a different page here. I'm going to say negative 470 for sodium hydroxide. And negative 286 for H2O. And the heat of reaction, excuse me, I'm going to go back here. The delta H of reaction is going to equal the products minus reactants. Well, this is a product, and that's a reactant. And if you notice from the previous reaction, there were actually integers in front. There was a 2 there. Okay, so we actually have to multiply our delta H by 2 as well. So we have to multiply that by 2 and that by 2. So the products, which are these guys, be 2 times a negative 470 minus 2 times a negative 286. You got to see what that equals, and then your final answer there would be number of kilojoules. Okay. Let's see what that comes out to if we do our math correctly. We're looking at negative 368 kilojoules. Okay, and again, the sodium and the hydrogen didn't really take part in that. All right, so I'm going to give you a little sample problem here. This is a little bit of chemistry in action. So we're going to look at this process using fuel values of foods and other substances. So we've got a process here where we got sugar, which you eat all the time. We all eat it all the time. It is hidden in all foods. That's glucose right there. Plus oxygen, so this is your body. It takes glucose and it burns it, and it produces CO2 and water and gives off a bunch of energy, obviously. Here's the energy. And that's what your body uses to get by from day to day. I'm going to look and ask you, okay, with a little bit of time, I want you to calculate, if we look at, this is cookies, right? This is 6 cookies, this box, right there. Okay, about 28 grams of cookies. The sugar, let's say that this is the total sugar, 7 grams. And that's kind of a lie, but we're just going to say that that's the way it is. We got 7 grams of sugar. All right, this delta H right here that we're looking at pertains to 1 mole of the sugar. We have 7 grams of this sugar. So go ahead, I want you to calculate out the total number of kilojoules that are produced. Okay, you got to turn this from grams to moles. Multiply it then by that over here. And then I want you to turn that into the amount of calories and see what you get. Okay? I don't know, this could be a fun little activity. See how many calories come from the sugar that's in this box. All right, that's all I have.